10,000 years is not a number that human intuition handles well. We hear it and we think of history, distant history, the kind that belongs in museums and textbooks, the kind separated from our daily lives by so many layers of language and technology and culture that it might as well be mythology. And yet, 10,000 years ago, our species was already fully formed. We had the same brains, the same emotional architecture, the same fundamental hunger to understand. We were farming, we were building, we were looking up at the same night sky you looked up at last night. The stars were identical. The moon rose and set just as it does now. The physics of light and gravity and time operated by the exact same rules that govern every atom in your body at this very moment. That is what makes 10,000 years such a uniquely strange distance to contemplate. It is long enough to swallow every civilization ever written about in any history book, long enough to bury cities under meters of sediment, to reshape coastlines, to reroute rivers, and yet it is nothing, a fraction of a breath on the timescale of stars. 10,000 years is so short that our sun has barely moved in its orbit around the Milky Way. It's so short that the nearest stars have shifted by only a few degrees in the sky. The universe, by any cosmological standard, has not changed at all. And yet, from a human vantage point, 10,000 years forward is so alien, so radical, so incomprehensible that it might as well be a different universe entirely. So what would it look like if someone, some being, some intelligence was standing at some point 10 millennia from now, looking back at us and recording what they see? What would that record contain? What would be worth documenting? What would remain of everything we've built and believed and loved? And more than that, what would the universe itself look like through their eyes? If you enjoy deep space explorations like this, consider subscribing. This is not a story about aliens. It is not science fiction, though it will feel like it. Every claim made in this narration is grounded in real astrophysics, real climatology, real geology, real evolutionary biology. What you're about to hear is, to the best of our current scientific understanding, the most honest portrait possible of what 10,000 years from now might actually look and feel like. And the result is something that should genuinely unsettle you in the best possible way, because it reveals truths about our present moment that we are normally too close to see. Let's begin not in the future, but in the deep past, because that's the only lens through which the scale of what we're talking about becomes emotionally real. Go back 10,000 years. The year is approximately 8000 BCE. The last great ice age is winding down. Giant glaciers are retreating from what will eventually become northern Europe and Canada, carving out valleys and fjords and the shapes of entire continents as they go. Sea levels are rising. They will rise by over 100 meters over the following several thousand years. As all that ice melts, Britain is still connected to continental Europe by a landmass geologists called Doggerland, a vast fertile plain now buried beneath the North Sea. The Sahara is green. It is in the middle of what climatologists call the African humid period, a time when monsoon rain swept across the region and vast lakes sparkled where today there is only sand. The Amazon basin is thick with pre-agricultural human settlements we are only now beginning to find traces of. The first cities are either being born or are about to be. Jericho has existed in some form for nearly 1,000 years already. The cultures that will eventually produce writing, mathematics, astronomy, philosophy, and every other intellectual tradition that flows forward into our present moment. They are here, right now, in embryonic form. They are people. They have names and families and arguments and jokes and grief. They look at the sky and wonder. They bury their dead and tell stories to explain the stars. And they have no idea, none, that in 10,000 years, their distant descendants will be sitting in climate-controlled rooms, staring at glowing rectangles, transmitting their thoughts instantaneously across a planet wrapped in invisible signals, occasionally escaping the atmosphere in small metal shells to float weightless in the void above. That gap between what those people could possibly have conceived and what we actually became, that is the gap we now have to project forward. Because if we are now to those ancient farmers what the humans of 12,000 CE will be to us, then trying to imagine the world 10,000 years from now requires us to fundamentally let go of almost everything we assume is permanent, starting with the sky. The night sky 10,000 years from now will be recognizably similar to the one we see tonight. This is one of the genuinely surprising facts about stellar astronomy. The stars are so impossibly far away that even their relatively fast by astronomical standards motion through the galaxy amounts to only small, angular shifts over 10 millennia. Orion will still exist. The Big Dipper will still be there, though it will be slightly distorted. The stars that make it up are at different distances and moving in slightly different directions, so over long timescales, the familiar shape bends and reshapes itself. By 10,000 CE, Orion's belt will have shifted enough to be noticeable to a careful observer comparing star charts, but someone glancing up casually would still recognize the constellation. What will have changed, however, is the pole star. Right now, we navigate by Polaris, the North Star, which sits almost directly above Earth's North Pole. But Earth wobbles. It precesses, like a spinning top that's been nudged, tracing a slow circle with its axis over a period of roughly 26,000 years. 10,000 years ago, the pole star was Thuban, a dim star in the constellation Draco. In 12,000 CE, the Earth's wobble will have moved the celestial North Pole toward Vega, one of the brightest stars in our sky, a brilliant blue-white gem in the constellation Lyra. Future navigators will look north and see not Polaris, but Vega burning overhead, brighter and more spectacular than anything we use for navigation today. If our imagined documentarian is making their vlog and they mention the North Star, they will point to a completely different object than we would. But let's not get too lost in the sky just yet, because the world below that sky will be almost unrecognizable. The first thing to understand is that we are living at an extraordinary geological moment. The Earth's climate has been remarkably stable for the past 10 or 12,000 years. Unusually stable, in fact, by the standards of the planet's longer history. This stability, which climatologists call the Holocene, is not the natural default condition of Earth. It is an exceptional interlude. Before the Holocene, the planet was locked in glacial and interglacial cycles, swinging between ice ages and warmer periods on roughly 100,000-year timescales, driven by subtle changes in Earth's orbit and axial tilt, a mechanism described by the Serbian mathematician Milutin Milankovic in the early 20th century. The question of what Earth's climate looks like 10,000 years from now is deeply, fundamentally tied to what we do in the next few centuries. This is one of the rare cases where the documentary script diverges into two possible timelines, because the physics genuinely allows for dramatically different outcomes depending on human choices made in the near term. The amount of carbon dioxide and other greenhouse gases released into the atmosphere in our era will continue to influence global temperatures for hundreds of thousands of years. Not centuries, not decades, hundreds of thousands of years. Carbon dioxide has a complex atmospheric lifetime, but a meaningful fraction of what we emit today will still be warming the planet in the year 12,000 CE. In the most optimistic realistic scenario, one in which human civilization transitions rapidly to clean energy and eventually begins to actively remove carbon dioxide from the atmosphere, the planet 10,000 years from now might look surprisingly familiar to Earth of today, perhaps a degree or two warmer on average, with somewhat different patterns of rainfall and drought, somewhat different coastlines due to continued slow sea level rise, but fundamentally recognizable. In the more difficult scenarios, the changes compound dramatically, and we'll come to those. But here's what geology tells us almost regardless of our choices in the coming centuries. 10,000 years is long enough for the planet's surface to change in ways that would astonish us. Mountain glaciers, not the polar ice sheets, but the smaller mountain glaciers that currently feed rivers across Asia, South America, and North Africa, will in almost all scenarios be dramatically diminished or entirely gone by 12,000 CE. The rivers they feed today, including the Ganges, the Yangtze, the Mekong, and numerous others that collectively provide fresh water for billions of people, will be fundamentally different in character, still flowing, fed by seasonal rainfall rather than glacial melt, but different in timing and volume and reliability in ways that will have reshaped entire agricultural traditions and urban geographies over the intervening millennia. Sea levels will be higher. By how much depends on the climate trajectory, but even conservative estimates suggest several meters of additional rise over 10,000 years. Major coastal cities of today, the places where human civilization has historically concentrated itself because humans have always been drawn to coasts for trade and food and transport, will be dramatically altered. Some will be underwater, some will have retreated inland, some will have built elaborate systems of barriers and pumps to maintain themselves against the encroaching sea. The geography of coastlines, which we tend to think of as fixed, will have shifted substantially enough that a map of the world in 12,000 CE would look meaningfully different from the one hanging on your wall today. And then there are the tectonic forces, which operate on timescales longer than 10,000 years, but which still matter at this scale. The Mediterranean Sea is slowly closing. Africa is very gradually colliding with Europe, and while 10,000 years is far too short for this collision to produce visible mountain ranges, the seismic and volcanic activity in the region, the earthquakes along fault lines, the occasional eruptions from volcanoes like Vesuvius and Santorini will have continued. The Pacific Rim will have seen dozens of major earthquakes. The Himalayan plateau, already the highest landmass on Earth, will be infinitesimally taller. These changes are tiny by geological standards, but meaningful over 10,000 years in terms of the landscapes through which rivers flow and the places where human settlements are safe or unsafe. What about the living world? What has evolution done in 10,000 years? The honest answer is less than you might think and more than you'd expect. Natural selection operates on generation times, and for large animals with long lifespans and slow reproduction, 10,000 years represents only a few hundred to a few thousand generations. That's enough to see meaningful adaptation to changed conditions, animals and plants shifting their ranges, populations adapting to new climates, species that are particularly sensitive to environmental change going extinct while others flourish. But it's not nearly long enough to produce new species in most large animal lineages by traditional speciation timescales. What is more significant is the role that human beings play in shaping evolution, a role that has been growing exponentially since the industrial era. By 10,000 years from now, the human influence on the evolutionary trajectories of every species on Earth will have been operating for over 10 millennia at industrial and then post-industrial intensity. The ecological niches that currently exist, the relationships between predators and prey, between pollinators and plants, between parasites and hosts, will have been scrambled and reshuffled many times over. There is a concept in evolutionary biology called the sixth mass extinction. The previous 5 were caused by asteroid impacts, volcanic super-eruptions, changes in atmospheric chemistry, and other non-biological forces. The 6th is the one we're currently driving through habitat destruction, climate change, overexploitation, and the introduction of invasive species to regions where they didn't evolve. And mass extinctions in the geological record are followed after timescales of millions of years by explosive radiations of new species that fill the vacated niches. 10,000 years is far too short for that radiation to produce recognizable new diversity from scratch, but it is long enough to see which generalist, adaptable species have surged into the niches left behind by the extinctions of more specialized species: crows, rats, coyotes, raccoons, cockroaches, pigeons, jellyfish, certain fast-reproducing insects. The survivors of mass extinction events throughout history share a family resemblance. They tend to be adaptable generalists, capable of eating a wide variety of foods, tolerating a wide range of temperatures, reproducing quickly, and living alongside other species without requiring specialized ecological partnerships. The diversity of the living world 10,000 years from now will likely be dominated by these kinds of organisms, at least in the places most heavily altered by human activity. Though in remoter regions, where natural habitats have survived or been deliberately preserved, biodiversity may look much closer to what we have today. And then there's the question that is perhaps the most interesting and the most uncertain of all. What about us? What does Homo sapiens look like 10,000 years from now? This question splits into two very different tracks, and which track is more relevant depends enormously on what happens in the next few centuries. The first track is biological. Biological evolution in humans over 10,000 years has historically produced real changes. The evolution of lactose tolerance in populations that domesticated dairy animals, the evolution of skin pigmentation, adaptations in populations that migrated to different latitudes, shifts in bone structure and immune system function. But natural selection requires differential reproductive success. Some individuals need to have more surviving offspring than others because of heritable traits. And in modern industrial societies, many of the traditional selective pressures have been removed or altered by medicine, agriculture, and contraception. This doesn't mean evolution has stopped. It means the selection pressures are different, and the traits being favored or disfavored are different. Precisely what those pressures are accumulating toward over 10,000 years is genuinely difficult to predict. The second track is technological, and this is where things get genuinely disorienting. We are living at what may well be the most pivotal technological moment in the history of our species. The development of artificial intelligence, genetic engineering, nanotechnology, and the possibility of brain-computer interfaces all suggest that the definition of human may be radically different in 100 years, let alone 10,000. If biological and technological integration continues, if humans begin enhancing themselves genetically, if interfaces between nervous systems and digital systems become routine, if medical technology begins extending healthy lifespan significantly, then the people of 12,000 CE may share our DNA in a technical sense while being so different from us in capability, cognition, and experience that they are effectively a different kind of being. But let's be careful here, because this is where the temptation toward pure science fiction is strongest, and where we need to stay anchored to what's actually physically plausible rather than what makes for a good story. 10,000 years is a very long time for a technological civilization to operate. The risk of catastrophic disruption, war, pandemic, climate collapse, asteroid impact, civilizational collapse of the kind that has befallen every major civilization in recorded history is not negligible over 10 millennia. There have been more civilizational resets in 10,000 years of recorded human history than there have been stable multi-millennial continuities. Every civilization we know of that has achieved a high level of complexity has eventually collapsed or transformed beyond recognition. This is not pessimism, it is archaeology. So, the honest documentary answer to who is our vlogger 10,000 years from now is, we don't know. It might be a being of extraordinary capability and sophistication, the product of 10,000 years of uninterrupted technological progress. It might be a human in the most traditional biological sense, living in a world that has rebuilt itself after one or more civilizational disruptions. It might be something in between, a technologically capable society that has advanced in some ways and regressed in others, as most real historical societies do. What we can say is this: if anyone is standing at a point 10,000 years from now, looking back at us, they will see us the way we see the people of ancient Mesopotamia. They will see us the way we look at the people who built Stonehenge, or the early farmers of the Fertile Crescent, or the first inhabitants of the Indus Valley cities. They will see us as the beginning, as the first awkward, fumbling, earnest, astonishing stage of something that became something else over a timescale. Their history books will treat as a single chapter, and what we've built, what we consider our greatest achievements, will appear to them in the way the mud brick walls of Çatalhöyük appear to us, not without meaning or dignity, but incomprehensibly remote and limited by comparison to what came after. Now let's turn away from the Earth entirely and look outward, because this is where the science becomes genuinely spectacular and the perspective becomes genuinely cosmic. 10,000 years from now, our solar system will still be our solar system. Nothing dramatic has happened to it. The sun is still burning, still fusing hydrogen into helium in its core at the same steady rate it has maintained for the past 4.5 billion years. It is about 4.5% older than it is today. a completely negligible change for a star in the middle of its hydrogen-burning main sequence lifetime. The Sun will continue burning stably for roughly another 5 billion years. 10,000 years barely registers. But there are subtleties worth noting, because even subtle changes are interesting at this scale. The Sun is not perfectly constant. It goes through cycles of activity, sunspot cycles of roughly 11 years, longer-term cycles on timescales of centuries, and perhaps millennia. We are only beginning to understand the longer cycles. Historical records and ice cores show evidence of periods of dramatically reduced solar activity, like the Maunder minimum, between roughly 1645 and 1715, during which sunspot activity almost completely ceased, and which correlates with a period of unusually cool temperatures called the Little Ice Age. It's not clear whether the Maunder minimum caused the Little Ice Age, or whether they were coincidental, or whether they were both driven by some other factor. But the point is that the Sun's output varies, and on timescales of centuries to millennia, those variations matter for life on Earth. Over 10,000 years, the Sun will go through many dozens of sunspot cycles, and possibly several longer grand cycles. In practical terms, this means that the exact energy output reaching Earth will fluctuate, adding another layer of complexity to the already complex picture of Earth's future climate. The planets continue their orbits. Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune, all still there, all still approximately where they are today. The orbital mechanics of the solar system are, over 10,000 years, extremely stable. There is no planet that's going to drift dramatically out of position in that time frame. The slight gravitational influences the planets exert on each other's orbits are real, but they operate on timescales of millions to tens of millions of years before producing significant instabilities. According to computer simulations of the solar system's long-term dynamical evolution, Mars, our nearest neighbor and the planet most often discussed as a potential site for human expansion, will still be Mars. It will still have its thin carbon dioxide atmosphere, its frozen water ice at the poles, its ancient dried river valleys, its towering extinct volcanoes, its vast canyon system that dwarfs the Grand Canyon. The question of whether Mars in 12,000 CE hosts human settlements is one of the most genuinely uncertain and fascinating speculative questions we can ask, because it hinges entirely on choices made and resources invested in our near future. Mars is hard. It is cold. Average temperature, roughly negative 60 degrees Celsius. It has almost no atmosphere to speak of, certainly not enough to breathe or to protect against radiation. Its gravity is only about 38% of Earth's, which has significant implications for long-term human health in ways we don't fully understand. The dust is chemically reactive in ways that are harmful to both machinery and biology. Despite all of this, our current technology is theoretically sufficient to send humans to Mars on survival missions. The engineering challenges are profound, but not fundamentally beyond what we know how to do. What they require is will and resources and a sustained commitment over decades. If that commitment materializes in the coming centuries, if human beings establish a permanent presence on Mars, if the population there grows, if generations are born on Mars who have never known Earth, then, by 12,000 CE, 10,000 years of human habitation on Mars would produce something genuinely extraordinary. A Martian civilization, separate from Earth's, adapted to Martian conditions, perhaps in the middle of a centuries-long terraforming project, or perhaps entirely abandoning that idea in favor of sealed underground cities or habitat domes, but distinctly Martian in culture and outlook in ways we can barely begin to imagine. And if it doesn't materialize, if for whatever reason the expansion of humanity beyond Earth stalls or reverses, then Mars in 12,000 CE looks exactly as it does today, dead, red, cold, and silent except for the wind. The same calculation applies with even greater uncertainty to the other destinations in the solar system that have attracted scientific attention. Jupiter's moon, Europa, with its global liquid water ocean beneath a thick ice shell, kept warm by the gravitational tidal flexing of Jupiter's enormous gravity. Saturn's moon, Enceladus, which has active geysers spraying water ice into space, also indicating a subsurface ocean. Titan, Saturn's largest moon, with its thick nitrogen atmosphere and liquid methane lakes, the only world in the solar system other than Earth with stable liquid on its surface. These are not places where you'd choose to build a city in the next few centuries, but 10,000 years is a long time, and civilizations that develop the ability to reliably travel and operate throughout a solar system have the entirety of those extraordinary environments available to them. The asteroid belt still drifts between Mars and Jupiter. Those rocks, ranging from tiny grains of dust to Ceres, a dwarf planet with a diameter of about 900 kilometers, represent an enormous repository of materials: iron, nickel, platinum group metals, water ice, silicates. A civilization capable of extracting and processing asteroid resources has access to a level of raw material wealth that completely dwarfs anything available on Earth's surface. One medium-sized metallic asteroid, a few kilometers across, can contain more iron and nickel than has been mined in all of human history. The economic implications of asteroid mining, if it becomes practical over the next few centuries, are staggering, and over 10,000 years, the degree to which humanity has developed the ability to utilize the resources of the asteroid belt will be one of the defining factors in what their civilization looks like. Beyond the asteroid belt, the gas and ice giants and their moons occupy a vast cold space that even optimistic projections don't see as heavily settled in 10,000 years. 10,000 years is simply not long enough, even at optimistic rates of technological development, for humanity to physically spread throughout the outer solar system at any density. The distances and the energy requirements are simply too vast, but probes will certainly have visited everything in exhaustive detail long before 12,000 CE. Whatever mysteries remain about the composition of Uranus and Neptune, the nature of Pluto and the other Kuiper Belt objects, the structure of the Oort cloud by 10,000 years from now, either we will have answered those questions through robotic exploration, or we will not have survived as a technological civilization. And then, beyond even the Oort cloud, which extends perhaps a quarter of the way to the nearest star, we reach the space between the stars, and here the scale becomes so enormous that it begins to produce a kind of quiet vertigo. The nearest star to our Sun is Proxima Centauri, a small red dwarf about 4.24 light-years away. A light-year is the distance light travels in 1 year, roughly 9.46 trillion kilometers. Proxima Centauri is therefore about 40 trillion kilometers away. Our fastest spacecraft, the Voyager probes launched in 1977, are traveling at roughly 17 kilometers per second and will take about 73,000 years to reach Proxima's distance, though they're not headed in that direction. With current propulsion technology, getting a probe to Proxima Centauri would take roughly 70,000 to 80,000 years. Getting humans there, with life support and sufficient shielding and the fuel to slow down on arrival, is at current technology essentially impossible. But 10,000 years is a long time for technology to develop. The theoretical limits of space travel are not set by our current engineering. They're set by physics, which is considerably more generous. A spacecraft accelerating at one Earth gravity for long enough can reach a significant fraction of the speed of light. The energy required to do so is immense, but not physically forbidden. Various exotic propulsion concepts have been studied seriously by physicists. Nuclear pulse propulsion, which uses the controlled detonation of nuclear devices to accelerate a pusher plate. Antimatter drives, which release energy at the theoretical maximum efficiency through matter-antimatter annihilation. Laser-pushed light sails, which could in principle be accelerated to a substantial fraction of the speed of light by powerful laser arrays. Ramjets that scoop hydrogen from the interstellar medium. None of these are buildable today. Some of them may be buildable in centuries. Whether any of them exist in 10,000 years depends, again, on whether technological civilization has continued to advance. If it has, if something like a coherent, expanding technological civilization has been operating in our solar system for 10,000 years, then it is plausible, though not certain, that interstellar probes of some kind have been sent toward the nearest stars. They might not have arrived yet, even at 10% of the speed of light, which would require an enormous engineering achievement. A voyage to Proxima Centauri takes 42 years. At 1% of the speed of light, it takes 420 years. Whether our civilization or its successors has managed to actually send such probes in the previous 9,000 years, and whether those probes have returned data, is one of the genuinely fascinating open questions about 12,000 CE. What about Proxima Centauri itself? It's a red dwarf star, the most common type of star in the galaxy. Red dwarfs are small, cool, dim, and extraordinarily long-lived. They burn so slowly that some of them will still be burning hydrogen 1 trillion years from now. Proxima Centauri has at least one confirmed planet in its habitable zone, Proxima b, a world of roughly Earth's mass orbiting its star at a distance that, given the star's lower luminosity, places it in the zone where liquid water could theoretically exist on its surface. But here's the crucial complication. Proxima Centauri is a flare star. It regularly produces intense bursts of ultraviolet and X-ray radiation that would strip the atmosphere from an unprotected planet over geological timescales and would render the surface of any planet in its habitable zone extraordinarily hostile to life as we know it. Proxima b is also almost certainly tidally locked, one face permanently turned toward its star, the other in permanent darkness, because at such close orbital distances, the gravitational torque locks the planet's rotation to its orbit within a geologically short time. Whether these conditions are compatible with life is genuinely unknown. We don't know if Proxima b has an atmosphere. We don't know if it has liquid water. We don't know if there is or ever was anything living on its surface. If we've sent probes to Proxima Centauri by 12,000 CE, and that's a genuine if, those probes will have answered the question of whether Proxima b is alive or dead in the most literal sense. That answer, if received, would be perhaps the most significant piece of information in all of human intellectual history. The confirmation that life exists elsewhere in the universe, even microbial life, even a dead biosphere preserved in rocks, would fundamentally transform our understanding of what the universe is and what it's for. The other nearby stars are not dramatically more promising, but they are extraordinarily interesting in different ways. Alpha Centauri, A and B, the two sun-like stars that orbit each other in a binary system at roughly the same distance as Proxima, with which they form a triple star system, are, in terms of stellar character, the closest analogues to our Sun in the entire sky. Alpha Centauri A is almost identical to the Sun in mass, temperature, and luminosity. Alpha Centauri B is slightly smaller and cooler. Whether either hosts planets and what those planets are like, we currently know only in fragmentary and contested ways. Detecting Earth-sized planets in habitable zones around the Alpha Centauri stars is at the very edge of current observational capability, and the data we have is ambiguous. But by 12,000 CE, any civilization with 10,000 years of technological development will have resolved these questions completely. The telescopes of 10,000 years from now, whatever form they take, will be as far beyond the James Webb Space Telescope as James Webb is beyond a handheld magnifying glass. The ability to directly image and characterize planets around nearby stars, to take spectroscopic readings of their atmospheres and look for chemical signatures of life, will be an engineering problem solved centuries or millennia before 12,000 CE if civilization continues to develop. Our vlogger, looking at the night sky, knows exactly what every star in the neighborhood has around it. They know the surface temperatures of dozens of nearby worlds. They know, or think they know, whether any of those worlds harbor life. And the Milky Way itself? What does the galaxy look like from the perspective of 12,000 CE? The structure of the Milky Way is something we've only begun to map in earnest in the past few decades. We live inside it, which makes the mapping problem genuinely difficult, like trying to draw the floor plan of a building while standing in the middle of one of its rooms, unable to step outside and look. But what we know is this: the Milky Way is a barred spiral galaxy, roughly 100,000 light-years across, containing somewhere between 100 billion and 400 billion stars. Our Sun sits in one of its spiral arms, called the Orion Arm or Local Arm, about 26,000 light-years from the galactic center. We orbit the center of the Milky Way once every 225 to 250 million years, a period astronomers call the galactic year or cosmic year. 10,000 years represents about 1/22 millionth of a galactic year. In terms of the galaxy's large-scale structure, absolutely nothing has changed by 12,000 CE. The spiral arms are exactly where they were. The galactic center, that dense, chaotic region surrounding the supermassive black hole called Sagittarius A star, is still there. Still 4 million solar masses of compressed spacetime, still occasionally producing intense bursts of radiation when it feeds on infalling gas and dust. But at the level of individual stars, the inhabitants of our galactic neighborhood, interesting things are happening. And here is where one of the most cinematic facts about 12,000 CE comes into focus. Stars move. They move relative to each other, orbiting the galactic center on slightly different paths at slightly different speeds. And as a result, the neighborhood of stars around our Sun is slowly shuffling. Over millions of years, stars drift in and out of our immediate vicinity, but 10,000 years is enough time to produce measurable changes in the distances of nearby stars, and one of those changes is genuinely dramatic. The star Gliese 710, currently located about 62 light-years away, a dim orange dwarf star in the constellation Serpens, is moving directly toward our solar system. Stellar astronomers have tracked its trajectory and calculated that in approximately 1.29 million years, Gliese 710 will make its closest approach, coming to within about 0.05 light-years of our Sun. That's deep inside the Oort cloud, the vast reservoir of comets in the outermost reaches of the solar system. Such a close stellar passage is expected to gravitationally perturb vast numbers of comets from their stable Oort cloud orbits and send them plunging inward toward the inner solar system, and producing a comet shower that could last tens of millions of years. But that's more than a million years away. What's happening in our stellar neighborhood? Over 10,000 years. Other nearby stars are drifting, some toward us and some away. Barnard's star, a dim red dwarf currently about 6 light-years away and the second closest individual star to the Sun, has the largest proper motion of any star in the sky, moving at about 10.3 arcseconds per year relative to the background. Over 10,000 years, it will have shifted noticeably. By 12,000 CE, Barnard's star will be about 3.8 light-years from the Sun, closer than it is today, before it begins to recede again. For a brief cosmological moment, a blink of geological time, Barnard's star will be our closest stellar neighbor, overtaking Proxima Centauri's current position. This matters not just as an astronomical curiosity, but as a fact about the geometry of interstellar civilization, if such a thing is being built. The nearest star is a moving target, and the target is different in 12,000 CE than it is today. Now, let's expand the view further still, out to the context of the observable universe, because this is where the narration takes a turn into territory that is, in the most profound sense, humbling. The universe is 13.8 billion years old. Our solar system formed 4.6 billion years ago. Complex multicellular life appeared on Earth roughly 600 million years ago. Homo sapiens appeared roughly 300,000 years ago. Written history is roughly 5,000 years old, and we are having this conversation at a moment about 10,000 years before the year 12,000 CE. Now expand the view. The observable universe, the sphere of space from which light has had time to reach us since the Big Bang, is about 93 billion light-years in diameter. It contains an estimated 2 trillion galaxies. Each of those galaxies contains anywhere from a few billion to several hundred billion stars. The number of potentially habitable planets in the observable universe is so large that it defies comprehension. Estimates range from 10 to the 20 to 10 to the 24. That is a 1 followed by 20 to 24 zeros. There are, by this accounting, more potentially habitable planets in the observable universe than there are grains of sand on all of Earth's beaches. And yet, as best we can tell, we are alone. Or at least, we have found no compelling evidence of anyone else. This is the Fermi paradox, named after the physicist Enrico Fermi, who crystallized it in a casual lunchtime conversation in 1950. If the universe is so vast and so old, and if the conditions for life are so widespread, and if intelligence and technology are achievable by biological evolution, as demonstrated by our own existence, then where is everyone? Why haven't we heard from anyone? Why haven't we been visited? Where are the signals, the artifacts, the unmistakable signatures of other technological civilizations? Our documentarian in 12,000 CE, standing 10,000 years further along in the search for extraterrestrial intelligence, will have a dramatically expanded dataset, 10,000 years of more sensitive radio telescope arrays, optical SETI searches, technosignature hunts across the electromagnetic spectrum, a direct examination of exoplanet atmospheres for biosignatures and technosignatures. All of this will have either produced a detection or deepened the silence. And the nature of that outcome, detection or silence, will be perhaps the most important fact about the universe that shapes the consciousness and culture of beings living in 12,000 CE. If they've detected something, a signal, a technosignature in the atmosphere of a distant world, an artifact in our own solar system left by a previous visitor, then the universe looks completely different to them than it does to us. The philosophical implications cascade outward without end. We are not alone. Intelligence emerges routinely from the conditions of the universe. There are others out there with their own histories and perspectives, and perhaps their own questions about us. If they've heard only silence, if 10,000 more years of searching have produced nothing but the deep quiet of the cosmos, then the silence itself becomes a more profound and unsettling fact. It suggests that the emergence of technological civilization is extraordinarily rare, perhaps unique to Earth, perhaps the first such emergence in the Milky Way's entire history. Or it suggests that civilizations routinely collapse before they can make themselves heard across interstellar distances. Or it suggests that the signatures of advanced civilizations are simply not what we're looking for, that the technologies used by a civilization a million years more advanced than us produce signatures completely outside our ability to recognize or detect. Each of these resolutions to the Fermi paradox carries different weight for what the cosmos means and what our place in it is. But here's the thing about cosmic silence that the astrophysics makes particularly poignant. Even if alien civilizations exist in abundance, the universe is physically expanding. And it's not just expanding, it's accelerating. The discovery of cosmic acceleration in 1998, for which Saul Perlmutter, Brian Schmidt, and Adam Rees received the Nobel Prize in Physics in 2011, revealed that the expansion of the universe is not slowing down under gravity, as most cosmologists expected. It's speeding up, driven by a mysterious energy that permeates all of space, which we call dark energy, and which comprises about 68% of the total energy content of the universe. The consequence of accelerating expansion is that distant galaxies are receding from us at velocities that exceed the speed of light, not because they're moving through space faster than light, which relativity forbids, but because the space between us and them is expanding, and at sufficient distances, the expansion of that space carries them away faster than any signal could ever bridge the gap. There is a sphere around us, the cosmic event horizon, beyond which we can never receive information, regardless of how sensitive our detectors or how much time we wait. Galaxies beyond that horizon are causally cut off from us forever. And here's the disturbing part. The event horizon is shrinking in the sense that objects near its current edge are moving toward irretrievable distance. Over billions of years, the accelerating expansion will push more and more of the currently observable universe beyond our cosmic horizon. But over 10,000 years, the change is imperceptible. The event horizon moves so slowly on human timescales that 10,000 CE and 12,000 CE are virtually identical in terms of what's cosmologically accessible. But the vlogger in 12,000 CE, knowing this, knowing that the universe is accelerating away, that the sky of the far future will be increasingly sparse as distant galaxies redshift beyond detection, carries a different weight than we do. We exist at a moment when the universe is still, in cosmic terms, young and relatively dense and legible. We can see 2 trillion galaxies. In a trillion years, a civilization's sky will contain only the few hundred galaxies bound together in the local group by gravity, the Milky Way, Andromeda, the Magellanic Clouds, and a few dozen dwarf galaxies. Everything else will be gone, receded beyond the horizon, invisible. The universe will appear smaller and simpler and quieter than it does to us. 10,000 years from now, none of this has yet happened. The sky is still full of galaxies. The universe still looks the way it does today, but the vlogger knows the physics. They know what's coming, on timescales vastly beyond any conceivable civilization. Yes, but they know, and that knowledge shapes how they see the night sky. Now let's talk about something that the physics of 12,000 CE makes genuinely exciting rather than sobering. What humanity might have learned about the universe in 10,000 additional years of scientific investigation. The history of science is a history of paradigm shifts, moments where an accumulation of evidence or a conceptual breakthrough overturns the previous understanding so thoroughly that the older framework looks almost naive in retrospect. Ptolemy's geocentric model gives way to Copernicus's heliocentric model. Newton's gravity gives way to Einstein's general relativity. The classical physics of matter gives way to quantum mechanics. Each of these revolutions didn't just add to the previous knowledge, they reorganized it, revealed it to be a special case or an approximation of something deeper. We currently have 2 theories that between them describe almost everything we observe: general relativity, which governs gravity and the large-scale structure of spacetime, and quantum field theory, which governs the behavior of matter and energy at the subatomic scale. These 2 theories are extraordinarily successful. Every experiment designed to test them has confirmed them, and they are profoundly incompatible. They work in different mathematical languages and make different assumptions about the nature of reality at the deepest level. Reconciling them, finding a theory of quantum gravity that supersedes both and explains the universe at all scales simultaneously, is the defining challenge of theoretical physics in our era. In 12,000 CE, one of 2 things will be true. Either we will have found that theory, a complete, unified theory of physics that encompasses quantum mechanics, general relativity, and probably dark matter and dark energy as well, or we will not have found it. If we have, the consequences for technology are incalculable. Every major physics revolution in history has led, within a few centuries, to technological applications that were unimaginable beforehand. The understanding of electromagnetism led to the entire electrical and electronic civilization we inhabit. The understanding of quantum mechanics led to transistors, lasers, MRI machines, and everything else built on semiconductor technology. A theory of quantum gravity, if it produces engineering applications the way previous physics revolutions have, could lead to technologies so far beyond our current capabilities that describing them in current language is nearly impossible. Or we may still not have found it. Physics doesn't guarantee discoveries on human timescales. It's possible that the deepest structure of reality is simply beyond our experimental reach, that the energy scales at which quantum gravity effects become observable are so extreme, so far beyond anything achievable in a terrestrial or even solar system scale accelerator, that we may never have empirical access to them. In that case, theoretical physics in 12,000 CE may still be debating versions of the same fundamental questions we debate today, armed with vastly more sophisticated mathematics and computational tools, but still without the empirical anchor that would settle the question definitively. The resolution of that uncertainty, known or still unknowing, is perhaps the most profound difference between their intellectual world and ours. But here's something the vlogger in 12,000 CE definitely has that we don't: 10,000 years of additional astronomical data. This matters more than it might initially seem. Many of the most important processes in astronomy operate on timescales longer than human civilization. We have been doing systematic astronomy with modern instrumentation for less than 200 years. To truly understand things like stellar evolution, galactic dynamics, long-period variable stars, the behavior of binary star systems over centuries, The statistics of rare astronomical events. To understand all of these properly, you need data covering much longer timescales. Consider supernova. A massive star ends its life in a supernova explosion after burning for millions to hundreds of millions of years. In our galaxy, which contains hundreds of billions of stars, supernovae occur at a rate of roughly 1 or 2 per century. Over 10,000 years, our galaxy will have produced roughly 50 to 200 supernovae, each one briefly outshining the entire galaxy in which it occurs, each one seeding its neighborhood with heavy elements forged in the dying star's core. Some of these may be close enough to affect Earth directly through the enhanced radiation environment they produce. Most will be safely distant, but all of them will be observed, catalogued, and studied in detail by the instruments of 12,000 CE, contributing to a database of stellar death events of incomprehensible richness compared to what we currently have. And consider what they know about neutron stars, the dense, its spinning remnants left behind by supernova explosions of certain types of massive stars. Neutron stars are objects so compressed that a teaspoon of neutron star material would weigh 1 billion tons. They spin up to 700 times per second. They have magnetic fields trillions of times stronger than Earth's. When two neutron stars spiral together and merge, pulled together by the energy they radiate as gravitational waves, a process that can take billions of years, they produce a kilonova explosion that briefly outshines many galaxies and is one of the primary sites of our process nucleosynthesis, the formation of the heaviest elements: gold, platinum, uranium, osmium, iridium. The gold in your jewelry was almost certainly made in a neutron star merger billions of years before the solar system formed. In our era, we detected our first gravitational wave signal from a binary black hole merger in 2015 and our first neutron star merger in 2017, a landmark event that was simultaneously observed across the electromagnetic spectrum, inaugurating the era of multi-messenger astronomy. 10,000 years from now, gravitational wave detectors of almost incomprehensible sophistication, perhaps space-based arrays thousands of kilometers or even light years in scale, will have detected millions or billions of gravitational wave events. The gravitational wave sky will be as richly mapped as the electromagnetic sky is for us. The vlogger's universe is a noisier, more dynamic, more violent, and more beautifully intricate place than ours appears from our limited vantage. There is one cosmic event worth discussing in detail because it sits on a timescale close enough to be on the minds of astronomers in 12,000 CE, even if it won't happen for billions of years. The collision between the Milky Way and the Andromeda galaxy. Andromeda, M31, is our nearest large galactic neighbor, approximately 2.537 million light-years away, a spiral galaxy comparable in size to the Milky Way, containing roughly 1 trillion stars. And it's coming toward us. Measurements show Andromeda approaching at roughly 110 kilometers per second. In approximately 4.5 billion years, Andromeda will collide with the Milky Way in a galactic merger that will eventually produce a large elliptical galaxy astronomers have nicknamed Milkomeda. The collision in 12,000 CE is still 4.5 billion years away, inconceivably distant by human standards. But astronomers in 12,000 CE will have measured it with extraordinary precision. They will know the exact geometry of the collision's approach, the timeline, with certainty to within millions of years, and they will have detailed simulations showing exactly how our region of the galaxy will be affected. The psychological weight of knowing that in a few billion years, your galaxy, your home, will literally be destroyed and rebuilt in a new form is something we are only beginning to grapple with in our current era, as our measurements have only recently confirmed the collision scenario. In 12,000 CE, it's been known for 10,000 years, and it's presumably a settled background fact of astronomical culture. Let's return now to the more immediate and personal scale, because the most emotionally resonant question about 12,000 CE is not about stars or galaxies or cosmic acceleration. It's about us, about what survived, about what was remembered. What do the people of 12,000 CE know about us? The answer to this question tells us something important about what we are doing right now and why it matters, or doesn't matter, as the case may be. Consider what we know about the civilizations of 8000 BCE. The answer is surprisingly little, and what we know is fragmentary, often ambiguous, filtered through the imperfect record of archaeology. We have their tools, we have their settlements, at least the ones that happen to be in places where stratified sediment preserved the remains. We have their bones, from which we can extract genetic information and learn about disease and diet and movement. We have traces of their art on cave walls and in carved figurines. We have no words, we have no names, we have no individual faces. The recording revolution of our era, the fact that we are generating more data in a single year than was generated in all of previous human history combined, suggests that our successors in 12,000 CE might know us in extraordinary detail. If the digital records of our civilization are preserved through whatever transitions and disruptions occur in the intervening millennia, they will have access to photographs and videos of essentially every person who ever lived during the digital era. They will have the text of hundreds of billions of conversations, documents, and works of art and literature. They will have the ability to reconstruct, with some fidelity, the inner lives of individual people living in our time. But data storage is not neutral. Digital formats become obsolete. Media degrades. Servers require power and maintenance. Institutions that preserve archives require stable funding and stable governance. Every civilization in history has lost the vast majority of its literary and cultural production. The Library of Alexandria, the libraries of the Mayan cities, the oral traditions of hundreds of cultures, all gone or nearly gone. The record that survives is always a small, biased, imperfectly preserved fraction of the whole. There is also the question of catastrophe. If civilization as we know it is disrupted significantly by climate collapse, by war, by pandemic, by any of the numerous plausible large-scale disruptions that 10,000 years provides ample opportunity for, then large portions of our digital record could simply vanish, inaccessible on degraded or destroyed infrastructure. Conversely, materials inscribed on durable physical media, stone, metal, certain ceramics, can survive for tens of thousands of years under the right conditions. The clay tablets of ancient Sumer, fired by the very fires that destroyed the libraries they were stored in, survived because clay tablets don't burn. A civilization 10,000 years from now that wants to know about us will have, in all probability, a patchy, uneven, and frustratingly incomplete picture. They will have some things in extraordinary detail, perhaps the works of major cultural institutions that were deliberately preserved, perhaps some portion of the scientific literature, perhaps genetic databases and archaeological records, and they will have vast gaps. The everyday lives of ordinary people in most parts of the world, the oral traditions that were never written down, the local and the personal and the intimate. In this sense, the relationship between us and the people of 12,000 CE mirrors the relationship between us and the people of 8000 BCE. They are our past in the same way we are their past, and the record of us that reaches them is incomplete in the same ways that the record of ancient civilizations reaching us is incomplete, filtered, fragmented, dominated by what happened to be preserved rather than what was most characteristic or most important. What might they consider us most significant for? What will history, from their vantage point, or say was the defining thing about the early 21st century? From a distance of 10,000 years, certain things that feel enormously important to us right now will likely fade into background noise. The political events, the elections, the wars, the cultural debates. These will be as remote and locally specific as the political intrigues of ancient Mesopotamian city-states are to us. Important in context, interesting to specialists, but not the headline. What they will remember, if they remember anything, is the transition, the moment when a species that had been biological for its entire evolutionary history began, for the first time, to deliberately and systematically reshape itself and its world through technology. The development of nuclear weapons, the first time in history that a species acquired the ability to destroy itself, the development of the internet and the resulting explosion of collective knowledge and connectivity, the development of artificial intelligence, the creation, for the first time, of intelligence that is not biological, the first human footsteps on another world, the detection or non-detection of life elsewhere in the cosmos, the great climate crisis of the 21st and 22nd centuries, and how it was managed or mismanaged. These are the events at the scale of civilizational significance. The historians of 12,000 CE, assuming they exist, will have chapters on these things. In the same way, we have chapters on the agricultural revolution, the development of writing, the Bronze Age, the Roman Empire. These are the moments of transition that matter across millennia, and perhaps, most significantly, the question of whether humanity expanded beyond Earth, whether we became, or failed to become, a multi-planetary species. Because if we did, if the expansion to Mars and beyond succeeded and produced genuinely independent civilizations, then by 12,000 CE, there may be multiple branches of humanity, or whatever humanity has become, in different places, with different evolutionary and cultural trajectories, perhaps in contact with each other through some form of interstellar communication, perhaps not. The divergence of human lineages into something like separate civilizations, perhaps separated by light years, would be the most dramatic biological and cultural event since Homo sapiens left Africa. And if we didn't expand, if for whatever reason the civilization of Earth remained confined to a single world for the next 10,000 years, then 12,000 CE sees us still here, still human in at least some recognizable sense, but confronting the reality that all our eggs remain in one planetary basket. An asteroid, a supervolcanic eruption of sufficient scale, a pandemic of sufficient lethality, a nuclear war of sufficient scope, any of these could end the story on a single planet. The knowledge of this vulnerability and the response to it will have shaped 10,000 years of political philosophy and technological development in ways we can only sketch in outline. Here's something the vlogger in 12,000 CE experiences that we cannot: the knowledge of how it went. We live in the uncertainty. We live in the moment where all the possible futures are still genuinely open. They know what actually happened in the intervening millennia, the choices made, the catastrophes endured, the achievements reached. They carry the weight of that history in a way we cannot, because we are still making it. There is something humbling about this in both directions. From their vantage, looking back at us, we are making decisions right now that they live with the consequences of. The carbon we emit, the technologies we develop or suppress, the conflicts we choose to pursue or resolve, the investments we make in science and medicine and space exploration, all of these become the givens of their world. In a very real sense, we are their ancestors, in the same way that the Neolithic farmers of 8000 BCE are our ancestors. We didn't choose our ancestors' decisions. They can't choose ours. And from our vantage, looking forward at them, imagining them, hypothesizing them, trying to understand what their world looks like, we are doing something that is fundamentally an act of imagination constrained by physics. We cannot see them, we cannot hear them, we cannot know what they know, or what they feel, or what they regard as obvious that we are still struggling to understand. All we can do is read the laws of the universe, extrapolate forward as honestly as we can, and sit with the strange and slightly vertiginous realization that we exist at one specific moment in a story that extends in both directions, far beyond our ability to fully comprehend. There is a type of star called a red giant. When a star like our Sun exhausts the hydrogen in its core, it expands dramatically. In the Sun's case, it will eventually swell to perhaps 200 times its current radius, engulfing Mercury and Venus and possibly Earth before shedding its outer layers as a planetary nebula and leaving behind a white dwarf, a dense, cooling ember of stellar material about the size of Earth. This transformation will happen to our Sun in roughly 5 billion years. But right now, in the sky of 12,000 CE, there are stars that will undergo this transformation within the next few million years, astronomically soon. The star Betelgeuse, the famous red supergiant in the shoulder of Orion, is already in the red supergiant phase and could go supernova at any point in the next 100,000 years, possibly sooner. When it does, it will appear in Earth's sky as bright as the full moon or brighter, visible in daylight, and perhaps for weeks. It will be the most spectacular astronomical event in recorded human history, and whether it happens in our lifetime or in the lifetime of someone in 12,000 CE or sometime in between is genuinely uncertain. The vlogger, looking at Orion, sees something we might not. They know whether Betelgeuse has already exploded. If it hasn't, if in 12,000 CE Betelgeuse is still there, still red and bloated and ominously bright in the shoulder of Orion, then the supernova remains an anticipated event, perhaps imminent on astronomical timescales, perhaps not for another 50,000 years. But if it has, if sometime in the previous 10 millennia, Betelgeuse went supernova and blazed across the sky, then the Orion constellation that the vlogger knows has a permanent, spectacular scar, a nebula in place of Betelgeuse, a beautiful, expanding cloud of ionized gas that will be visible for tens of thousands of years, one of the most striking objects in the night sky. This is the kind of specific, contingent knowledge that makes the vlog from 10,000 years in the future so fascinating to think about. Not just the general trends, not just the broad brushstrokes of cosmic evolution, but the specific, accidental facts about which events happened when, which stars exploded, which probe reached which star, which civilizations rose and fell, whether anyone found life around Proxima, whether the Martian colony survived, whether the artificial intelligence that was created in our era became something wondrous or something terrible or just something pedestrian, a tool, useful and unromantic, the way electricity is a tool. All of that is unknown to us and known to them, and the gap between what we know and what they know is the shape of the next 10,000 years of human experience. One thing we can say with confidence, rooted in physics, is what the night sky looks like from Earth or from wherever humanity has settled. In 12,000 CE, the stars are slightly shifted from their current positions, with Betelgeuse either still present or replaced by a nebula, with Vega now the North Star rather than Polaris, with Barnard's star slightly closer and therefore slightly brighter. The planets are still there, orbiting in their familiar paths. The Milky Way still arches across the sky on a clear dark night, a river of light containing hundreds of billions of suns. And if you were standing somewhere on Earth in 12,000 CE and looking at that sky, if you had somehow been transported there from our present moment, the sky would feel familiar, not identical, but recognizable. You would find the constellations, slightly altered. You would find the Milky Way. You would find the moon, still there, still roughly the same apparent size in the sky. The moon moves away from Earth at a rate of about 3.8 centimeters per year, so in 10,000 years, it will be only 380 meters farther away, completely imperceptible. You would look at that sky, and you would feel the same things humans have always felt looking at the sky: smallness and wonder, and the curious ache of knowing that the light reaching your eyes from those distant suns has traveled for years and decades and centuries, and carries no message from anyone, but feels like it should. Our vlogger, recording their observations of the cosmos, carries all of the accumulated knowledge of 10,000 additional years of science and exploration, and possibly interstellar observation. But they still look up, they still feel it. Whatever they have become technologically and biologically and culturally, they are still, in some meaningful sense, the descendants of the people who scratched cave paintings onto stone walls and stacked rocks into circles and argued about the nature of the universe in marketplaces and university halls and late-night conversations. The curiosity doesn't go away. The wonder doesn't go away. The desire to document and share and communicate, to make a record of what you've seen and what you understand, that doesn't go away either. That's what the vlog from 10,000 years in the future actually is, at the deepest level. It's not a technology demonstration. It's not a display of how much has changed. It's a continuation of the same impulse that's driven humans to make marks and tell stories since the beginning of our species. The desire to say, I was here, and this is what I saw. And here we arrive at something that deserves to be said clearly and without any softening. The universe does not care. It is not indifferent in a cruel way. It is simply not the kind of thing that cares. The stars burn because nuclear physics compels them to. The galaxies drift apart because dark energy compels them to. The atoms in your body will disperse long before the sun expands into a red giant, scattered back into the interstellar medium from which they came. He eventually incorporated into future stars and planets, and perhaps future beings. The universe will continue without us, as it continued before us. But consciousness is here. Awareness is here. The capacity to experience wonder, to ask questions, to build instruments that extend our senses across billions of light years, to construct mathematical frameworks that describe the behavior of things that happened before the Earth existed. This is here. It emerged from the physics. It wasn't placed here from outside. It is what physics does, in at least some places, under at least some conditions. And whatever the universe is for, a question that may be fundamentally unanswerable, consciousness appears to be one of the things it produces. The vlogger, in 12,000 CE, is that same phenomenon, 10,000 years further along, still conscious, still asking questions, still looking at a sky filled with light from distances so vast that the travel time of that light exceeds the entire length of human civilization, still trying to understand. And they are recording it, documenting it, sending it forward, as we send things forward, in the faith or the hope, or simply the habit of believing that someone on the other side of time will watch and listen. Consider the golden records aboard the Voyager spacecraft. Those two identical records launched in 1977, now beyond the edge of the heliosphere, traveling through interstellar space. They carry greetings in 55 languages, 116 images, 90 minutes of music, sounds of Earth. They were designed not for any specific recipient, but as messages in a bottle thrown into the cosmic ocean, with the knowledge that they would drift for billions of years without likely being found by anyone. And yet, we made them. We etched the instructions for playing them in a form that any sufficiently intelligent species would be able to decode. We chose the music and the greetings and the images with extraordinary care, because the act of making them, of trying to communicate across unimaginable distances and timescales, was itself meaningful. The vlog from 10,000 years in the future is that same impulse in reverse. Someone, some being, some intelligence 10,000 years downstream, making a record of what they see and know, directed at no one in particular, or maybe at us, aware that we exist in their past the way the Voyager launches exist in ours, making the record because the record is meaningful, regardless of whether it's received. We should talk for a moment about something more speculative, but physics adjacent. What happens to information over 10,000 years? Not just cultural information, the records and documents and memories, but physical information in the technical sense used by physicists. In classical physics, information is conserved. The state of a physical system at one moment in principle contains complete information about all past and future states. But in practice, information is extraordinarily fragile. Complex systems, like civilizations or ecosystems or individual human lives, are thermodynamically open and generate enormous amounts of entropy, the measure of disorder. The particular arrangement of matter and energy that constitutes you, reading these words at this moment, will never be exactly recreated anywhere in the universe. The specific pattern of neural firing that constitutes your experience of reading these words, the specific emotional resonance of this exact moment that is happening once and only once in all of time and space. This is not cause for despair, it's cause for paying attention. The vlogger in 12,000 CE is similarly unique. Their specific experience of a universe 10,000 years older than ours, whatever that experience is, whatever they feel when they look at a sky where Vega is the North Star and where some nearby star may recently have exploded, that experience is singular. It will never happen again. And if they're recording it, making their vlog, their document, with their mark, they're doing what we do when we make documentaries and art and scientific papers, trying to transfer the specificity of that singular experience into a form that can be transmitted and preserved, knowing that something is always lost in translation, but doing it anyway. There's a concept in physics called the light cone. Everything within your past light cone is in principle able to have influenced you. It's the region of space-time from which information could have traveled to your location at or below the speed of light. Everything within your future light cone is in principle able to be influenced by you. The boundaries of your light cone define the limits of your causal reach. The light cone of the vlogger in 12,000 CE is centered on a different point in spacetime than ours, displaced 10,000 years forward. Their past light cone is enormous. It encompasses our present moment and everything in our present moment that has or will send a signal into the future. Every photon that leaves your body, every gravitational wave generated by any mass you set in motion, every electromagnetic signal you produce, all of this is inside their past light cone. In principle, traces of us are accessible to them. The light from our cities has already left Earth and is currently traveling at the speed of light in all directions. In 10,000 years, that light will have reached stars up to 10,000 light years away. A sufficiently sensitive telescope on a world 10,000 light years away could, in principle, be watching us right now. And similarly, our vlogger's past light cone extends back to include all of human history. At every light second of history that has unfolded on Earth and in the solar system over the past 10,000 years is in principle accessible to a sufficiently sensitive observer anywhere in space, encoded in the light that has left our planet at every moment of that 10,000-year span. We exist, all of us, in an enormous web of light-encoded history, rays spreading outward from every event at the speed of light in all directions, carrying diminishing, but never quite zero information about what happened, where, and when. The universe is full of these signals, overlapping, ancient, some of them carrying information about events that occurred before the Earth formed, carrying the fingerprints of stellar explosions and galactic mergers, and the earliest moments of structure formation after the Big Bang. The vlogger in 12,000 CE has 10,000 more years of this data than we do. They are embedded in a richer signal environment, surrounded by more history, looking at a universe that has done 10,000 more years of things. And yet, they look at the same fundamental laws we do, the same speed of light, the same quantum mechanics, the same thermodynamics, the same space-time geometry described by general relativity, or they look at whatever deeper theory has subsumed those laws, which will still be consistent with everything our laws describe, because our laws work extremely well. In the end, what is the deepest truth that the vlog from 10,000 years in the future reveals? It reveals, I think, that the universe is not finished. 10,000 years from now, it is still going. The story is still happening. Stars are still forming in giant molecular clouds where gravity is overcoming thermal pressure and turbulence. Planets are still accreting in the disks around young stars. Life, wherever it exists, is still evolving. Civilizations, wherever they exist, are still building and breaking and rebuilding. The cosmos has not arrived at any endpoint. It has not wound down. The arrow of time still points in one direction. Entropy still accumulates. But within that general drift toward disorder, extraordinary local pockets of complexity, of which conscious beings are the most extraordinary known examples, still emerge and flourish and ask questions. We are not the end of something. We are somewhere in the middle of something whose end we cannot see and whose beginning we can barely sketch. The vlogger in 12,000 CE is further along in that middle than we are, but they too are in the middle. 10,000 years from now, the universe's age is 13.8 billion plus 10,000 years. It is still, by any cosmic standard, young. The longest-lived stars, the small red dwarfs, will burn for trillions of years. The universe has a future extending across timescales that make 10,000 years look like nothing, because it is nothing in those terms. And yet, it matters. It matters from the inside. It matters to us, right now, in our specific location, in space and time. It matters to whatever being stands in 12,000 CE, recording their experience of the cosmos. The mattering is not diminished by the scale. If anything, it's amplified by it, because consciousness arising in a universe this vast, this old, this physical, this law-governed, and yet this surprising, is a phenomenon of almost implausible improbability, and something improbable that exists is not less precious for its improbability. It is more precious. The night sky tonight is the same night sky the vlogger will look at in 12,000 CE, give or take a few degrees of stellar drift. If you go outside on a clear dark night and let your eyes adjust and look up, really look past the light pollution, past the familiar planets, past the atmospheric shimmer, you'll see something that has been seen by every human being who ever lived. The same stars, the same darkness between them, the same slightly bewildering sense of depth and scale and silence, and you'll be looking, though you cannot know it in any direct sensory way, at a sky that already contains the light that will reach Earth 10,000 years from now. The photons arriving at your retinas right now were emitted by their stars hundreds or thousands of years ago. The photons arriving at the retinas of beings in 12,000 CE have already left their sources. They are already on their way. The light connecting us to our successors, mediated by the stars, is already in transit. This is the physics of continuity. We and the vlogger of 12,000 CE are not separated by an unbridgeable gap. We are connected by the same physical universe, operating by the same laws, woven together by the same threads of causality and light and gravity. The 10,000 years between us is not empty. It is full of things, events and choices and discoveries and catastrophes and new life and lost traditions and rebuilt cities and launched probes and expanded understanding, full of people who will love things and build things and wonder about things and tell stories about things. Our story and their story and the universe's story, which contains both. The vlog from 10,000 years in the future exists, not in any server or on any screen in our present, but in the sense that 10,000 years from now, if consciousness persists, someone will be in a position to make it. They will know things we don't and lack things we have. They will carry our legacy and be shaped by our choices, and they will look at the stars and feel something we would recognize, however different everything else about them might be. And if we could watch it, if by some impossible means the documentary record of their universe could reach us, we would see, I think, not an alien world, but a familiar one, viewed from an unimaginable distance. The universe, still gorgeous, still enormous, still full of questions, still, somehow, home.